Okay, and our final speaker in this session will be Xingda Wei from Shanghai Jiaxin University, talking about how transactional memory can be used as part of a distributed transaction system.
Thanks for the introductions. Here I'm with pleasure to present our work on improving the in-memory transactional processing using advanced hardware features. This is a joint work with Jiaxin, Yanzhe, with our advisors Rong and Haibo. So in-memory transactional processing is very important in many daily lives online transactional processing workloads, such as e-commerce systems or railway ticketing systems. They typically require to handle billions of requests per day over a large volume of data. So this kind of workloads require us to run fast transactions on a cluster of machines, and thus necessitate distributed transactions. However, many scalable distributed transactional systems have very poor performance. For example, they typically can execute 100,000 of transactions per second when only using a lot of machines. Thus, they require a high cost, which means that they require a configuration of a large number of cores to outperform their single-threaded counterparts. On the other hand, there are some single machine transactional systems which can execute the same amount or more transactions per second, but they are not designed to be scaled out, which causes dilemma in the performance of single-node transactional system with the scalability of a distributed transactional systems. In a prior, Michael Stormberg has analyzed why current database transactions or distributed transactions are slow. In his analysis shows that many time are spent in things such as buffer pooling, logging, and latching. So only 4% of workload time is spent on useful data processing. On the other hand, we have noticed that there are many advanced hardware features available for us to use. One example is hardware transactional memory, which allow a group of load and store instructions to be executed in an automatic, consistent, and isolated way, whose ideas originates from database transactions. Another example is remote directory memory accesses, which allow cross-machine accesses with high speed, low latency, and low CPU overhead. So these two features give us opportunities to rethink the design of a low-cost and scalable in-memory transactional system. More specifically, HTM provides strong atomicity, which means that a non-transactional code will unconditionally abort a transaction when their accesses have conflicts. And RDMA provides strong consistency, which means that one-sided RDMA operations are cache coherent with the memory accesses at remote machines. So the HTM's strong atomicity combined with RDMA's strong consistency means that RDMA one-sided operations will unconditionally abort and conflicting HTM transactions, which forms a basis for a preliminary distributed transactional memory. So based on the above observations, our overall idea is to use HTM's ACI properties for local transactions execution. And we further use these one-sided RDMA operations to group multiple HTM transactions together to support distributed transactions. By this means, local transaction can directly leverage HTM for concurrency control at very low cost. And a distributed transaction can leverage both the feature of HTM and RDMA. Hence, in our system, the buffer pooling overhead is reduced by in-memory store. The logging overhead is reduced by in-memory logging to a non-volatile memory. The locking overhead is reduced by one-sided RDMA operations, and the latching overhead is reduced by HTM's features. So based on above all, we design and implement DrTM, which provide fast distributed transaction using HTM and RDMA. We are targeting on online transactional processing workloads over a large volume of data. There are two components in our system, a transaction layer and a memory storage layer. For transaction layer, each transaction request will be dispatched to a worker thread at one of the machines, and that worker thread will execute the transaction through completion using our concurrency control schema. For memory store layer, it provides a general key value interfaces for the transactions layer to use. We can achieve over 5 million new order transactions for TPC-C when only using 6 machines. So I will start from our concurrency control method in transaction layer. There is some problem of directly using HTM and RDMA operations to execute all transactions. Since first, HTM is only a compelling hardware feature for single machine platform, a distributed transaction cannot directly get benefit from it, since HTM cannot detect conflicts at remote machines. And second, with the implementation restrictions of HTM, some instructions and system events, such as RDMA network request, will unconditionally abort this HTM's execution. So we cannot directly use RDMA operations inside an HTM transaction. So how to glue multiple HTM transactions together by RDMA while preserve serializability is our first challenge. We solve this problem by using an RDMA-based two-phase locking schema to transform a distributed transaction to a local transaction which can use HTM to execute. The idea is we first using two-phase locking to accumulate all remote records of a transaction prior to the accesses in an HTM transaction. So for example, if we want to execute a transaction, we'll first log its remote data records at remote machine and then fetch them back to a local cache. Then we'll start an HTM transaction to execute the original transaction logic. Thus, in the HTM transaction, the remote data records can be directly operated on local cache. So there's a limitation in our schema since we have to know the whole read-write state of each transaction in advance, similar with previous work. However, we found it holds for many online transactional processing workloads. So combined with two-phase locking, here is how concurrency control works in DrTM. The coordination of local transactions are provided by HTM, and we use two-phase locking to coordinate distributed transactions. It is trickier to coordinate local transactions with distributed transactions. There will be two scenarios. First, a local transaction is executed before a distributed transaction. So here, if a conflict happens, the local transaction would be aborted by the distributed transaction due to the hardware features of RDMA and HTM. And the second scenario, where a distributed transaction is prior to a local transaction. So at this time, the local transaction needs to check whether its data record has been locked or not, so as to detect remote conflicts. However, this check is very simple since we only need to check whether the data is locked. With a local transaction, do not need to lock the data record. The second challenge is with the semantics of RDMA operations. RDMA generally provides 3 network interfaces. And here we want to use RDMA one-sided operation as much as possible, since it has better performance and can function without the assistance of a remote processor. However, RDMA one-sided operations provide a limited interfaces for us to use, namely read, write, and automatic compare and swap. So how to support exclusive and shared logs in two-phase logging schema using RDMA one-sided operation is our second challenge. As we noticed that RDMA's automatic compare and swap implements the same semantic as a local processor's compare and swap. So it is easier to implement the exclusive log. So in DrTM, we use this primitive to implement a spin log for our exclusive log. However, it is harder to support a shared log due to RDMA operations' less expressiveness. We use a lease-based protocol to support a shared log. So a lease will guarantee that a data record will not be modified until its expiration. A transaction can set or read back a lease for shared logs acquisition. And there's no need to invalidate or release the lease when the transaction commits, since this lease can be shared by other transactions. So we reserve the field at each data record's metadata to set the lease's end time, which corresponding to the shared log state in the two-phase locking protocol. And we use RDMA's automatic compare and swap to set the state of data record automatically. Here, we use each machine's machine time to set the list and to check whether a given list is valid or not. Since machine time may have deviation in a distributed settings. So we solve this problem by first, we use a time synchronization protocol to minimize the deviation among machine time in the cluster. And second, we use a delta to tolerate the possible deviation among checks. So for example, if one machine wants to decide whether a given list is expired or not, it will compare its current machine time with the list's end time plus a delta. And only if the current machine time is larger, it will think the list is expired. So it can maybe set it to an exclusive mode or do other things. So based on above, let's see how a transaction is executed in DrTM. So there are three phases in a DrTM transaction's execution: the start phases, the local transaction phases, and the commit phases. So in start phases, given the all remote read-write set of this transaction, we will use the corresponding method to set them in an appropriate mode according to their access patterns, and then fetch them back to a local cache. Once all remote data of this transaction has been accumulated, we'll use xBegin to start an HTM transaction to execute the transaction logic. Here comes the local transaction phase. So during the execution of local transaction, we provide a read-write interface for each data's accesses and modifications. For remote data records accesses and modifications, it can be directly operated on local cache, since the remote data has been safely locked at remote machines. For local operations, we need to further check its conflicts between remote transactions. So we will call the corresponding local read and local write operation. For local read operations, we need to check whether data has been in an exclusive mode or not, since we need to avoid a dirty read. And for local write operations, we will further check whether the data has been set in a valid list or not, since we cannot directly modify a read-locked object. So notice that all these operations are executed in an HTM transactions. So we do not need to detect conflicts between local transactions, which is done by the hardware at very low cost. So once the transaction finishes, it will come to the commit phase. Since we use lists as our shared log, so we have to make sure that all lists are valid at commit time, which corresponding to that in two-phase locking, all read logs must be released at the shrinking phase. So we insert an invalidation before we actually commit the transaction's result. Since we use list's end time to mark a list, so it is sufficient for us to check whether the minimal list time acquired by this transaction is valid or not. And once this check passes, we can safely commit this transaction's result. So first, we'll use xn to excite HTM transaction and commit local modifications to the main memory. And then we'll use release write back to write back the remote modifications, which is stored at local cache to the remote machine and release the remote logs. So that's how the transactions are executed in DrTM. There's some challenge of supporting durability using our concurrency control schema. Since first, we are using HTM transaction to execute all the transactions. So once a HTM commits, the results of a transaction can be observed by other machines. So we have to make sure that once the HTM commits, that the transaction's results will be eventually committed, even there is machine fail. And second, since a machine's data record can be modified by other machines without its awareness, so a single machine can no longer solely log all its accesses to its record. So how to provide durability with our concurrency control schema still has some problem to fix. We use a cooperative logging and in-memory logging schema to provide durability. So for in-memory logging, we will log the modification of a transaction to a non-volatile memory in HTM. So here we assume a flash on failure policy, which means that the HTM transactions writes to a non-volatile memory will be persisted once the HTM transaction commits, even there is machine failures. For cooperative logging, each transaction will log its log set before it actually executes transactions. So when machine is recovered from failure, it can release the remote logs it acquired. So once a failed machine needs to be recovered, all the surviving machines in the cluster will be notified to help recover the data record at this machine by draining their logs. So there will be 2 logs for each transaction, one for logs acquisition and one for data modifications. And only if both logs exist, we'll think that a transaction is committed. So that's all about the transaction layer of DrTM. Next, I will talk about our memory stores designs. DrTM provides an ordered store and an unordered store according to database tables access patterns. For those tables requires range queries, we provided an ordered store where each partition is stored as a local B+ tree, similar with DBX B+ trees. So here we do not optimize RDMA operations for ordered store, since in our workloads, there's no inevitable remote accesses to an ordered store. And an RDMA-friendly ordered store is still a challenge for us. For an unordered store, we provided an RDMA and HTM-friendly hash table. Although RDMA-friendly hash table has been well studied, in DrTM, we have different scenarios than the previous designs. First, since you are targeting a symmetric model where each node is both a server and a client, so we want to use one-sided RDMA operations as much as possible. And second, most accesses to the memory store is local accesses within an HTM transaction. So we want our memory store to be friendly to local operations and to HTM. So previous designs usually uses some complex hash structure so as to improve the RDMA lookup performance. However, this hash structure may sometimes hard to fully leverage HTM for insertion. And they only uses one-sided RDMA operations for data lookup and data fetch. They offloaded the modifications to host machine for the ease of risk detection. And they also do not provide RDMA-friendly caching schema, since content-based caching is hard to implement efficiently, especially when using RDMA operations. So in DrTM, when RDMA combined with HTM provide a new design space for us. So we use in DrTM, we use a simple hash structure as we can fully leverage HTM for the insertion and deletion. We decoupled the risk detection from memory store layer to the transaction layer so that we can use both one-sided RDMA read and write operations. We further provide a location-based cache, which can improve the RDMA lookup performance. I will start with our hash structure. So in DrTM, we use a variant of traditional chaining hash table with associativity, which we call cluster chaining. We decoupled the memory region to store the index structure and the data record with a shared indirect header to achieve high space efficiency and better RDMA lookup performance. So although very simple, in our micro benchmark, we show that our hash structure have similar performance with previous hash structure used in RDMA-friendly stores. So in this table, we show the average RDMA operation lookup time among these 3 hash structures. And as we can see, in both uniform and skilled workload, hopscotch hashing and our cluster hashing can have better performance than cuckoo hashing, since doing both these hash structures will fetch a lot of key value pairs when using one RDMA read. Hopscotch hashing performs slightly better since it has better space utilizations. However, our class hashing structure is much simpler and can always leverage HTM for insertion. As we further notice that the best RDMA lookup time is 0 if we can know the location of a remote key in advance. So we provide a cache at each machine to cache the location of remote keys. So you can think of at each machine, we keep a partially styled snapshot of the global hash index structure. So once a remote key's location is cached at local, it can be directly operated using one-sided RDMA operations without lookup overhead. So it is important to keep the cache transparent to the host so as the normal operations will add no overhead. So since we use a location-based cache, so there's no need to invalidate the cache entry when there are data modifications. So you only need to detect the stale cache entry when there is insertion or deletion. So here we use an incarnation schema so that each client can detect whether its cached entry is valid or not. So our cache size is very small since we only cache the location of each data record. And it can be shared among all the worker threads at the same machine so that it can be filled really quickly. So in our micro benchmark, we show that the average lookup cost is 0.178 for a skewed workload. We use a 20 megabyte cache starting from empty, which shows that our cache schema is really efficient. So finally, we show that the RTM's key value store with caching can provide a comparable performance. So in these figures, we show how throughput changes with value sizes and how latency changes with throughput. We compare the RTM's key value store with caching with other RDMA-friendly hash tables. And we use purple line to mark our hash structure. So this is a uniform workload, and the cache is starting from an empty state. So as we can see in this figure, that the RTM's key value store with caching can achieve the lowest latency and highest throughput. So there are some other implementation issues which is related to our hardware platform. So due to time limitations, I will not talk about this in detail. So if you have interest, you can refer to our paper. So finally, I will talk about our evaluation. So in our evaluation, we want to show that by fully leveraging the advanced hardware features, our system can achieve a better performance than the previous designs. We use Kelvin as our comparison since it has the best reported TPC-C results for a distributed system during our research. So all the experiments are carried on a local cluster with 6 machines. We use Intel's RTM as our HTM platform, and each machine is connected with RDMA network. We use 2 popular online transactional processing benchmark, TPC-C and SmallBank. We first show our performance on TPC-C. In the left figure, we show how our throughput changes when we add more machines to both systems. Each machine is configured to use 8 worker threads. And as we can see that both machines can have a good scalability. And when using 6 machines, the RTM can outperform Kelvin by 18 times. This is because although in the same hardware settings, Kelvin's design do not fully leverage the advanced hardware features. In the right figure, we show how throughput changes when we add more worker threads to each machine. So we use 6 machines for this test, and we do not compare Kelvin in this evaluation since it is hard-coded to use 8 worker threads. So as we can see, the RTM can scale up to 8 cores. The reason for the performance drop when there are more than 8 worker threads is that there will be cross-socket accesses, and since currently our memory store is not NUMA-friendly. Fortunately, since we noticed that TPC-C is a well-partitioned benchmark, so we can avoid most cross-socket accesses by deploying a DrTM instance at each socket. So the result system, DrTMS, can scale up to 16 threads, and it can outperform Kelvin by 27 times when using 6 machines. Further, we show that we can have a good scalability on TPC-C using a simulated test. Since we only have 6 machines, so we deploy 4 logic machines at each physical machine, and the logic machines are configured to use 4 worker threads. Notice that all the communications between the logic machines are going through the network card using RDMA operations. So in this figure, we can show that when up to 24 machines, the RTM can scale out well on TPC-C. Next, we show our performance on SmallBank. As we can see, when there is not much distributed transactions, the RTM can scale out and scale up well on SmallBank. And when there is more distributed transactions, the RTM can scale out steadily when there are more than 2 machines and scale up steadily in the same socket. So finally, I will show how our performance changes when we enable logging for durability. So we use TPC-C for this test, and we use a machine setting with 6 machines, and each machine is configured to use 8 worker threads. We use a dedicated DRAM to emulate a non-runtime memory. And as we can see in the table that our throughput dropped about 11% when we enabled logging. The performance drop is mainly because that there are more writes in an HTM transaction, which will cause more HTM's capacity abort. However, we think this performance drop is acceptable. So while the RTM makes a first step on combining HTM and RDMA for low-cost transactions, it still has some limitations. So we plan to further fix them in future work. So in conclusion, we have seen today that with advanced hardware features such as HTM and RDMA opens new design spaces for us. So the RTM's concurrency control and its memory storage layer fully exploits the advanced hardware features, and we achieved an order of magnitude higher throughput than the previous system. So that's all. Thank you very much.
Indy Gupta, University of Illinois. It seems to me, it's wonderful to optimize throughput, but it seems to me like your abort rates are a little bit high, 40% or so. I'm wondering if you can say what the liveness properties are. Are transactions ever starved?
Sorry, your question is that the abort rate is too high in our test in this.
Right, and what liveness properties do you guarantee for transactions?
Sorry,
What liveness property do you guarantee? Is a transaction guaranteed to commit if it keeps retrying? What is your liveness property?
So there will in implementation. In our implementation, we implement a fallback handler, which will guarantee the liveness of HTM transaction forward progress. So if the abort time exceeds a threshold, we'll use a two-phase logging schema to execute all the transactions. So it will guarantee liveness.
Dushyant Narayanan, Microsoft Research. When you do your lease checks, you have this delta. How do you calculate delta? I mean, you have to make sure that's bigger than the time difference between any 2 machines.
So you mean how we set the lease interval for delta?
Yeah. How are you synchronizing your clocks to within this constant always?
So there are some background thread will coordinate the soft time among machines, and the leases will always larger than the delta, and typically it's much longer than the delta, since the delta will be not very large, because we are in a local cluster and the time deviation will not be very large. So,
But does your clock synchronization have a guarantee that?
Yes. So we use a PTP protocol which can guarantee which can make a test about what's the deviation of machine time in the cluster, which is about 200 nanoseconds in our cluster. So it can guarantee this. So because our lease interval delta will typically be microseconds, so it will be much longer than the deviation for time.
Okay, thank you.
Christopher Mitchell, NYU. Your paper seemed to imply that RDMA can invalidate hardware transactional memory transactions. Is that the case? And if so, how does that work?
So you mean if RDMA cannot work with
if an RDMA read occurs on an area of memory that's locked by an HTM transaction?
You mean an RDMA read will, so during each RDMA read we will first lock the data items either in an exclusive mode or in a shared mode. So then we will fetch the data items and operate on them. So.
Okay, thank you.
Okay, thank you.